Okay, hold on. I mean, this is going to take a moment. But in any case, okay, so this is an idea, anyway, to use these more complicated seeds. Now you should go on and talk about, and then talk about a few other things. I mean, this is something I can work on. Let me just see. All right, anyway, we're about to see the result. Well, no manifolds there would be my expectation. We got that nice creature. Okay, what makes a cage? I mean, we got that thing, but that thing we've already seen. Yeah, you see these? Those are, I mean, those we've...
Well, this is clearly just doubled because of initial condition.
Yes, but the question is whether... So, I mean, the next case would be... Oh, for God's sake. I'm going to delete this from this notebook. This is silly. It's silly to just store this, just piles and piles of stuff here. Oh, for goodness sake. It's rendering 2 copies of that. Okay, in any case. So do you think we should do triple here or even more? Or do you think it's not going to make any difference? I think it's not going to make any difference.
Well, it seems to me with this kind of rules, it's just going to triple the whole thing.
It's what? It's just going to triple.
Actually, that's pretty obvious. It's going exactly the triple of it. There's nothing else that could happen.
I agree. So the only case that's going to be interesting, well, what about that thing?
Well, it's tripled again.
Yeah, fair enough. Okay, so the first case that could be interesting is a 2-2 goes to 3-2. Do you agree?
Yeah.
Well, is it obvious that they can't lead to anything more interesting, even if the rules on the right, even if the initial condition is, no, it is obvious. Yeah, it's obvious. Okay, so the next case of interest is 2-2 goes to 3-2. And conveniently, we have a 2, 2 goes to 3, 2 right there. Oh, gosh. I have to rewrite the test connected. Yeah, we have to rewrite this a bit. Let's not go through this right now. Okay, let's talk about some other physicsy things, and then I'll do this. Okay, so
incidentally, so this seed manifold idea. So this works in the case where you have a rule that effectively preserves it. You know, if you have a Riemann volume form, it will preserve it. And so if you start from a seed manifold, you're always going to get a seed. You're always going to get a manifold out.
Yes.
But that's only a sufficient condition for a manifold limit.
That is correct. But so what do you think? Okay, so do you think you have a theorem about when it preserves manifoldiness? And what do you think? I mean, clearly, I would hardly consider this creature a very convincing manifold.
No, right. So I think, I'm not sure if I ever put it in the Dropbox, but I sent it to you. The Olivier Ricci curvature of directed hypergraphs paper. You know, that there is a theorem on, you know, effectively when an arbitrary metric space can be considered, you know, to limit to a Riemannian manifold. And they even have the particular statement of that for hypergraphs.
Okay,
but
so what's true for the loops back on itself hypergraph? I mean, in other words, apply that theorem to this hypergraph, to the self-loop hypergraph.
Yeah, I would assume that's not a manifold under this definition.
Let's find out.
I can check it.
Yeah, why don't we check that? Because, you know, in the once a manifold, always a manifold theory, right? This is clearly making a manifold, but this wasn't, unless that thing says that this was a manifold even at that stage.
Then we have some emergent feature of the rule.
Yeah. It's a emergently manifoldian rule. Now, obviously, the interesting question is, what happens if we go to 4 of these? Does it...
Actually, one thing that I think we should try is to start with completely random. Start with a random graph, which is definitely not a manifold, and also not small, and see whether it will make a manifold out of it.
Whether this rule will make a manifold out of it.
Yeah.
Okay, so look, this appears to have a critical number of initial things of 6 that it needs in order to make a manifold. But let's see if we feed it 7, what it will do. Whether it will be greedy, so to speak.
What do we feed it 5?
I did feed it 5. Oh, look, if you feed it 7, it gives the same result. Let's try feeding it 8.
Well, with 5, it does a line, is it?
Yeah, that's right. 6 is the critical number then.
What about 4?
It did nothing. It made a this was the case, where was it? That was the case of 5.
4, yeah, okay.
4 is there. But actually, that's interesting because it makes a one-dimensional manifold effectively.
No, I suppose the 5th one doesn't matter. 4 makes a linear manifold, and 5 doesn't matter. Similar as 7 doesn't matter here.
Right. So the question is whether. Oh, what is that? Look at that. Look at that. Do you see that little orbiter? See that guy there? Okay, so
it kicked it out.
Yeah, right. So it just rejected that. This rejects something that can't be made into the manifold. That's pretty obnoxious of it.
That's a very clever rule.
It's a very, you know, it's insisting on traditional calculus-based mathematics.
Yeah.
It's ejecting.
Can we prove this is the minimal rule that understands differential geometry?
I'm sure it isn't the minimal one. I mean, but that is really amusing. So now the question is there any number for which it does?
What about 8?
I did 8. That's what this is. Okay, let me
both of them.
let me try code here. Sorry, just a second. Let me just rewrite this with code.
Yeah, let's just do it for all of them, the 1 to 10 or something, and see.
I will.
How much it rejects.
Okay. Let's do. Okay, we'll do 5 steps, and we will do.
We can have a list plot of the size of rejected component.
Yes, we can do that. Okay, hold on. Let's just make. I don't know. We don't really have good code for. Let's just do this visually to begin with. Okay, so table. I'm just going to superstitiously do this up to from 0 to 12.
It might be a bit much, but let's see. Oh, actually, it's only 2 inputs, so it should be fine.
Conveniently, I've got 12 cores on this machine. Actually, I did 13 here, so up. Okay, so it really is pretty much insistent on this structure, and it's just rejecting a little rosette there.
Yeah, for 12. It's interesting.
You think we should go, well, let's see, what was it? It was 6,
well,
right?
Because 12, it's double of the minimum.
Right. So
it doesn't make them into 2.
So let's just go, let's just for the hell of it, let's go 13 to 20, just in case something happens there.
Well, I see, it doesn't make it into 2 because there are only 2 4 edges.
Right, or 3 edges rather.
Well,
so we probably, let's try the different case. Let's try.
But then we start with 3 edges.
Yeah. And let's see how it ingests things there. Then I think it'll have more of an appetite then. My gosh. Oh my gosh, what is that creature? Well, the main thing we're learning is that seeds matter. Let's try the 4. Let's try. So.
Yeah, it's funny how we give this colored rule incorrect inputs and producing something interesting out of them.
All right, so let's do the following. Let's make a table of those, and let's give it 6 of these and half a dozen of the other. No, let's do n there. What was that in there? Oh yeah, that's the label. Okay. All right, so this is now trying, I'm just going to try up to 6 of those triple edges. Oh boy, what's that thing? So that's with 6 triple edges and 6 double edges, right? It's as if, okay, so there's a critical number of triple edges to start from. So I wonder what that turns into, if anything. Maybe we should just go 1 more step, 2 more steps. you think that's going to manifoldify or not? I think it's dead.
I vote not, yeah.
It's dead. I think it didn't have enough two-edge food. So let's go to 12 two edges and see whether that gives it enough food. This is oh. That's very bizarre. Look at that. So with 4 triple edges, okay, and
Oh, that's exactly double.
yeah, right.
Which makes sense.
And this is a weird object with the spoon universe.
Well, isn't it joint manifold with this word that it was making before?
Yeah, I think so. Okay, but it's
well, now we have space that changes dimension from place to place.
That's true. That is interesting, isn't it? That is interesting. So the only question is whether this has any sort of transition to a higher, you know, this thing seems to be a two-dimensional surface here.
Right.
And the question is whether it goes to anything more than that. But, okay, so I mean the basic, okay, this question about seeding, okay, so my question for you, Jonathan, is in this definition of, you know, discrete Ritchie curvature, what is the minimal thing that is considered a manifold by that definition?
Yeah, that's what I'm trying to work out, but it's, yeah, it's a complicated problem. I'll have to get back to you on that.
Okay.
And yeah, because this is written by fairly mathy people, of course, they have no explicit examples.
Right. Can be considered a discrete manifold. Should we just take a quick look at that paper? I think I have it in the Dropbox.
Yeah, yeah, sure, go for it. So it's there's the general metric space definition, but the one that we really care about is definition 3.2.
Which one is it? Hypergraph metrics?
Hang on, wait, sorry.
Yes, this one.
Yes, that's the one. Yeah, so 2.1 gives a general definition for metric spaces, but the one that we care about is 3.2, which is the specific, which is the specialization of that to hypergraph. So, I mean, it allows you to determine curvature of hyperedges, but
if all else fails, young Catherine is coming over here later today. She's good at reading these kinds of horrific definitions and might be capable of decoding. Let's see. Oh, for goodness sake. What does it have to do with probability measures?
So, well, actually, so the probability measure is a generalization of the notion of a volume measure. That part actually makes sense. I mean, the idea.
What is it?
Well, this is the thing. It's you don't know a priori, which is why it's hard to determine whether these things are, will limit to manifolds. Because basically, what you're saying is, obviously in the Riemannian case, you have a volume form. In the general metric space case, you just have a probability measure that will degenerate to a volume form in the case of Riemannian manifolds.
Okay, but let's understand what that is. What is that probability measure? Because one of the things I was going to bring up is I was just looking at random graph theoretic properties, including ones I don't understand very well, like local clustering coefficients and things like this, for the graphs that we're generating. So my question is, in a sense, there are many ways to probe a graph.
Right.
Okay. And for example, one way to probe a graph is to like do harmonic analysis or something and solve some, solve some PDE on the graph effectively, solve some discretized PDE on the graph.
Right.
And the question really is and so our notion of dimension is, I don't think it's equivalent to one of those things, but maybe these guys are saying that it is. But my question is, if you take a graph and, for example, you solve Laplace's equation on the graph, or you look at the spectrum of some operator on the graph, right? What does that tell you about the graph? Like, for example, from the spectrum of an operator, I bet you can tell things about genus.
Yes, yeah, that's probably true.
Right, with some a Singer index theorem-y like thingy or something, or so that's a question of whether, because so here's the bigger question. The bigger question is, what is the mean field theory of these graphs?
Right.
Okay, so what we're asking is, so if we imagine a cellular automaton, I mean, the mean field theory of a cellular automaton is pretty bad, but it's nevertheless fairly clear what it is. That is, you just take the probability of a particular value. So here, what I'm assuming is you take the probability, I mean, what you care about is the application of the rule, I think. So one thing you could do is you ask the question, what's the probability that the rule applies?
Right. So obviously, in the case of this paper, they're not considering any kind of dynamics. So it's completely independent of the update rule.
No,
so
I understand that.
The probability measures, as the measures are defined, is you say, take two vertices. Well, okay. The context in which this is relevant is if you want to generalize the notion of taking kind of metric balls around two close points. In which case, the idea is you pick two vertices, x and y, and then you define probability measures, mx, my, that correspond to random walks that start at x and y.
Okay.
That's the essential idea.
Okay, fine. So you have those random walks. Now, those random walks will probe something not unlike our volumes.
Right. Well, yeah, exactly. I mean, the idea is in the case where where it limits to a manifold, it will be exactly the volume.
Where what is the volume? What is the thing you're measuring for the random walk?
You're measuring. So if you have these two random walks, you can compute a Wasserstein distance between them, and then 1 minus the Wasserstein distance with some normalization gives you the curvature. And the claim is that in the Riemannian case, this is exactly the Ricci curvature. Okay,
so hold on. Let's take this a little bit more carefully. Okay.
Yep.
So forget a random walk. Let me just solve the diffusion equation.
Okay.
Because I can define a diffusion equation by starting with a delta function at one vertex. And then we can clearly make a coloring of the graph that solves the diffusion equation over time, right? So we run a certain number of steps. And in particular, we could solve the diffusion equation by relaxation if we wanted to have a sort of numerical method. We simply take, at every step, every node gets the average of its neighbors. Right? Okay. So now we have some distribution on the graph. And let's say we started it from two different points. Okay, then what? So this graph, so it's diffused out on the graph, and clearly the density at any given point. So let's say we have, if we had conservation, if we had a rule that, which we don't with this, well, actually, maybe we do with the right kind of relaxation, we have a conservation of stuff. So let's say we start with 1 unit of stuff at the center, and then we go for t steps, and we look at, then in a sense, in a dimension d thing, we know that we're going down, it's an inverse r to the d law, I think, for how much stuff you get on each of the tendrils.
Right.
Although it may not be uniform like that. It may be clumped up in some way.
Mm-hmm.
Okay, so now what is the definition that these guys are giving for given two of these distributions? What do they do with them?
Yeah. So suppose you have two distributions around points x and y.
Yep.
And you're interested in evaluating the Ricci curvature in the direction xy.
Okay.
Then what you're saying is, if we take the Earth mover distance, the Wasserstein distance, between those two distributions, and then you do 1 minus that divided by...
Remind me what that definition would be. So we've got for every edge on the graph, or for every node in the graph, we've got a number.
Right. And then if that number is associated with the weight, then the distance between them is the total work done in transforming one of those distributions into the other.
Okay, but okay, so you're saying we take every node of the graph, it has a value v sub I. Okay,
yes.
Actually, let's say from distribution 1, it has value, a sub I. Distribution 2, it has value b sub I.
Right.
Okay.
So if there's a correspondence between a sub I and b sub I.
No, the i's are the same.
Right.
The I just is a vertex index.
Okay.
Okay, so you're saying this is the sum of some absolute value of a sub I minus b sub I. Is that correct?
Multiplied by the distance.
By what distance? Oh, between
the two points. So we're assuming that the metric on this is every edge is unit distance.
Okay, so there's a geodesic distance between the 2 points.
Right. So we're effectively transporting some quantity from one node in one distribution to the analogous node in the other distribution, and the question is kind of what's the total amount of work needed to do that? And so it's the quantity multiplied by.
Okay, but I mean this thing where we are putting let's just understand this diffusion idea. Okay, so we have from a given node in the graph, we look at the diffusion of stuff away from that node. Okay.
Right.
Now the question is, can we use that in some way? So one thing we could do is look at for every node in the graph, after a while, there's been a bunch of diffusion. I mean, this reminds me of the PageRank computation.
Right.
After a while, there's been a bunch of diffusion, and there could be accumulation of, and in that diffusion, there is a, if the graph, for certain graphs, well, I mean, okay, let's assume the graph is undirected. If the graph is directed, it could just transport that stuff all over it.
Mm-hmm.
Okay? But assume it's undirected, then we're asking the question, what is the distribution? One question we can ask is, what's the distribution of density? We start from a given node and we wait for a while. Now, it is my conjecture that one of the handy-dandy graph measurement things that we already have is exactly that. So what do you think any of these are? I mean, one of these I predict is going to be essentially this. What is vertex eccentricity? Okay, mean graph distance is the mean distance between all pairs of vertices. Okay, but so what about the distribution of graph distances? Is that of interest? The distribution of graph distances should be a measure of dimension, shouldn't it?
Right. Well, yeah, dimension should be recoverable, or pseudo dimension.
Right. So that is otherwise known as just the histogram of the graph distance matrix.
Right.
Right. But okay, so we should look at these. But then, so what is that histogram? If we take, let's take one of these guys. Oh, we don't have that. Well, I have to convert it from a hypergraph. Actually, we already have that. Hold on. Let's take a look. Well, okay. Is it obvious what the, given the graph distance matrix, I think the histogram will be itself an R to the D type story, right? Because if it is uniformly of a certain dimension, then that means that there will be up to the edge of the graph.
There'll be an R to the minus D sort of character to the distance matrix.
Or is it R to the D? Because given a particular node, the number of nodes you get to that are distant.
Well, yeah, will be R to the D.
So I think it's an R to the D, and then it will crash and burn at some point at the end. So if we look, for example, at I actually need to switch computers. Hold on. Let me just I'll be right back. I'll switch computers. I'll see you in a moment. That's weird. My Zoom session was in a weird place here. Okay. Let's see. Still with us?
Yep.
Okay, so now the claim would be, let me make myself a note. To fix the colored network simplification. Okay. Okay. Let's. By the way, you do have the URL of this thing, don't you, Jonathan?
I do now.
Yeah, let me send it to you. Yeah, I'll put it in the chat.
I'm sure I've already visited. Yes, I know I already have it.
Okay.
Thanks.
And it works even on a phone. Okay, hold on. Let me just start this. Quit that. Oh, what's that?
The status not our universe. Is that new? I don't remember seeing that before.
Yeah, that was added. I mean, it's been added by default to all of them, but that has to be modified. Oh, the other important thing is we need to start searching for causal invariant ones. And are you in a position to search for causal invariant Wolfram models?
If the multi-way system code for the Wolfram model states graph is working correctly, then yes.
Okay, but that depends on the find hypergraph isomorphism, doesn't it?
It does. Yeah, so the current situation is the causal invariant thing doesn't work for the Wolfram model, or fails for some Wolfram model cases because the states graph for the multi-way system fails for certain Wolfram model cases.
Have you done any search for causal invariant ones?
I mean, I did a very, very small search as a way of debugging, but no, I haven't done anything serious.
Okay. And what we currently believe about that is that any single edge rewrite is causal invariant. Is that true?
Yes, I think that's true.
Although it's uninteresting because it has a tree causal graph.
Exactly. It's causally invariant because no non-trivial interactions can occur.
Right. Okay. So then the next case, you believe the causal invariant is always contingent on the initial condition. Is that a true statement?
No, because purely constructive rules would be causal invariant.
Yeah, exactly. I mean, yeah, there do exist rules where the causal network will always be a tree independent of initial condition, and purely constructive rules, as Max says, would be one example of that.
Yeah, but okay, what we want are causal invariant rules for which the causal network is not just a tree.
Yeah, exactly. So I think in general, we have to care about
rules. So it can happen.
By the way, do I need to install a new packlet here?
Well, I didn't update it, but let me put the new version which has accessors for evolution properties.
Okay.
So I have to do that.
Let me just store something away, and then I want to go back to this computation, which I think we're going to get somewhere with this manifolds and so on. Okay, so. Okay.
Just a moment.
Okay, so we've claimed here that non-overlappingness is contingent on particular initial conditions. So the first claim is, with a single edge initial condition, single edge LHS, all rules are trivially causal invariant, but give tree causal networks. Okay, so the claim is, non-overlappingness is contingent on the particular initial conditions, but there could still be causal invariance even without that. There could be causal invariance without non-overlappingness, right?
Right. Which is the case that's hard to test.
Right. But then, that could be independent of initial conditions. Is that true or not?
Yes, I think so. I don't have an explicit example.
Okay, do we have any constructed examples here? Now, in the case of strings, what is the relationship between causal invariance and non-overlappingness?
They might be equivalent in the case of strings.
I don't think so, because if you have AAA goes to AAA, that would be overlapping but causal invariant.
Okay, so AAA goes to what?
AAA.
What?
Or, well, you can also have AA goes to AA.
Yeah. Oh, I see. That's, you claim, well, if we had, well, just AA goes to, no, I see, we need 3. Do we need 3?
No, actually 2 also works.
Okay, so that is causal invariant.
Oh, that's even better, because it doesn't do anything, but it's overlapping.
I mean, it doesn't do anything.
Oh, AA goes to AA. It's obviously cause invariant because it does nothing. And nevertheless, it's overlapping.
Right. Okay. So how do we test? Do you have something which tests for causal invariance for the string case, Jonathan?
Yeah.
So have we run that?
I
bet it's in the NKS book, actually, this particular thing. Let me just take a look here.
Okay. But I mean, the deployed causally invariant queue should work without issue for strings.
We have this stupid problem again, this stupid problem. Sorry, just a second. Fortunately, I have my in case of emergency. Equipment here. Sigh. Now I actually should connect because I have 48 cores I can use altogether. I probably should connect them all. Okay, so you claim, let me just look in the NKS book before we go searching for this stuff, because I think I already had some things on that. Does anybody know whether that is in?
I found some code for checking non-overlapping string rules in the NKS, in the notes section.
Yes.
But I didn't find anything for testing general causal invariance. But maybe I didn't know where to look.
I haven't a clue anymore. I call them general substitution systems. Okay, so I obviously have had code for making causal networks from what I call general substitution systems. So I have to go find that. Although that code, this should be easy for us to do from, well, I'm not sure. Okay. I'm sure I must say if there are causal invariant ones here. Examples of two different ways. Okay. Great. All right. Okay, so that's an example. Oh, look. Oh, that's AB goes to, but that's a non-overlap rule, right?
Right.
Well, maybe I believed that there weren't any causal invariant ones except for the non-overlap. Oh, that's an interesting issue. That's an interesting claim. That the lambda calculus, well, I guess we knew that lambda calculus has one. All right, okay, so you claim.
Yeah, that's Church-Rosser.
Yes, that's the original Church-Rosser property.
Confluence Mark 1.
I've probably told you my stories about Berkeley Rosser.
I'm not sure you have, actually.
I met him once, nice old chap. And then I was visiting Madison, Wisconsin, actually right before my oldest child was born, so that means 23 years ago.
Mm-hmm.
And I knew he was based there, and so I tried to get in touch with him. And my then assistant contacted, a J. Berkeley Rosser at the university there, and that person said, "Well, actually, I'm the son, and I'm an economics professor."
Oh yeah, John Berkeley Rosser, Jr.
Okay.
Right, yeah.
Okay, and the father had died a few years earlier. But then I was at some used bookstore there, and I ended up buying all these logic books there. And then, like 5 years later, I opened one of these books on its, the inside cover was, a J. Berkeley Rosser signature or stamp or whatever. So I realized that I had unwittingly gone to a used bookstore in that town and bought a bunch of his books. So that's my connection. So I have a bunch of J. Berkeley Rosser books.
Nice.
Okay, let's take a look. So what is the name of your causal invariance checker?
It's, much to your derision, it's causally invariant Q.
Okay, so it's resource function of causally invariant Q. Okay, what does it eat?
So it takes the same arguments as multi-way system. So it takes a rule specification, an initial condition, and an iteration count, step count.
Okay, so have you done the obvious search?
In the string case?
Yeah.
No.
Okay, so for example, if I go AB goes to BA, and now, but wait a minute. The question of whether it does it independent of, okay, so wait a minute. What's it going to do here? So let's say I say 5 or something here.
Right.
Okay, what happens if I say 2?
It should also be true.
Okay, but so the search, what would we do to do the search? You have to enumerate possible rules.
Right.
And the first non-trivial one, okay, so let's take something which does have overlap. What is it going to do if I say AA goes to AA?
It should say that's causally invariant, I hope.
Okay, so what's the first non-trivial case? I mean, yeah, we would like to get a string case that is, I mean, you think there will likely be both contingent causally invariant things contingent on the initial condition and ones that are not contingent, right?
Yes, I think that's true.
All right, well, is your causally invariant queue fairly efficient?
Well, it's as efficient as our string multi-way system code, because that's the most algorithmically non-trivial bit. The thing that causally invariant queue is actually doing is a post-processing step on that, which is just checking for convergence of critical pairs. That's very fast. The slow part is generating the multi-way system.
Okay. Right. But now here.
But that generates multi-way system for double number of steps, as far as I understand.
Right, right.
What does this do? This was string tuples. Did I put this in the function repository? I think I did. Oh, for God's freaking sake, why is that not found? Great. I thought I had deployed that. Anyway, okay, we can look at this separately. Just Let's see, string causal. Okay, all right. So we were looking back at the at that manifold thing, right? So, but really, what we were the thing we were interested in was I was starting to look at graph features. So I was, okay, here I've got a convenient graph. And what we were talking about was the diffusion equation effectively on that graph.
Right.
Okay, so and oh yeah, we were going to do the graph distance histogram. Okay, so this, we can say graph distance of that graph, and then we just say, oh no, graph distance matrix of that graph, and we just say flatten that. And then we say make a histogram of those. Okay, what do you think this is going to look like? Why is it taking so long? Oh, wow. What does that mean? Well, let's take a different I mean, that looks quite Gaussian.
Right.
Let's take a different case. What would you like to take? Well, we could take one of the ones we've just generated over here. We could take that guy. Okay. What is your prediction here? I predict it's not going to be Gaussian.
I think it might be.
Drum roll. See, because I think this is somewhat related to, okay, so the criterion for a mean field theory. Oh, come on, this is taking forever.
It's quadratic.
How many nodes does this creature have? Is this thing a histogram of graph distance matrix? Is that one of the other measures? Vertex eccentricity.
I presume that's average distance from a vertex to other vertices.
Do you think it's that?
I assume so. Hang on. Yeah, the length of the longest, shortest path from the source to every other vertex. That's not an average here.
Ba ba ba.
Interesting.
That is very interesting.
Yeah, what the hell does that mean?
It means it's not a random graph, which we can plainly see. Whereas the other one is a fairly random graph. Now, the question would be, if we take the histogram of the distance matrix.
Can you plot range all of this histogram? I think it misses most of it. Huh.
Apparently not.
I'm confused by
there
that.
are distances. Wait, really? The largest distance is 7.
That does seem very bizarre, doesn't it? I mean, so if we take the graph diameter, it's not a directed graph, is it?
Well, it is to an extent.
No, but I mean,
actually,
the question.
Yes, we should be careful with this.
So, I mean, here, we probably should say, why was that so much faster? That's interesting. Okay, so this is the undirected case. Okay, so let's go here. I think that's our problem. Interesting. I think that that is a sign of the dimension of the graph.
What, the bias, you mean?
Yes, I think the long pieces are irrelevant. I think they're just seeing the edge of the graph.
Right.
I think what's interesting is that growth rate.
Yes.
There, which in this case looks like that, and in this case is convex. So let's pick another. So what is this? What is this? And is this some quantity that is otherwise? So the graph diameter here is like 80. The graph diameter here is like 10. Well, we can clearly run a bit more of this. We could run up to like 25 or something. So we say, what is this going to look like? Oh, wow. Look, that's becoming skew, but with a different curvature. Let's try running for 30 steps. Yeah, 30 steps, why not? Okay, but so this is just graph distance. An alternative would be, for every node of the graph, relax for a certain number of steps, starting off from a delta function.
Right.
Okay, so start from a delta function at a given node, then relax for some number of steps. Okay, so then there's a distance measure, as you say, then a way to compute distance between nodes is the extent of overlap of these distributions.
Yes.
And that is a kind of a softening of the pure geodesic distance, I claim.
Right.
Okay, so a separate issue is mean field theory. And I claim the main issue is what is the probability that an event happens in a given part of the graph? I claim is the main question for mean field theory. And if an event happens, what's the probability? Think about making like a transport theory thingy on this, where, okay, so think about it in terms of collisions of particles or something. I mean, in other words, if an event has happened, what then is the new form of the graph, and what's the probability that an event will happen in the same place? What is it? You know, okay, so an event happens, and that's like a collision taking place.
Right.
And it's putting things into different parts of phase space somehow. An event is analogous to, e.g., collisions. So what is the analog of f of p in, okay, who here remembers transport theory? Anybody want a quick recap on how that works? So the basic thing is you define a distribution function like f of p that defines the probability to find a particle at a certain momentum. And then the collisions, the probabilities of collisions are f of p1 times f of p2. And they lead to other momenta, p3 and p4. And so in other words, what you're doing is you're taking, in that particular case, but in our case, we have a single event that's happening. So we have a probability. Okay, so given, if we had a bulk property of the graph that says the probability for that implies the probability for an event. So let's consider that in the string case. Yeah. Look, in the strings case, consider a local entropy measure. We're asking, or some other measure, some other aggregate measure on n tuples. Then the question of whether the thing has, so I'm saying that we don't know if a specific sequence will occur, but we're making an aggregate statement about probabilities of an n tuple.
Right.
Okay, so let's be more specific there. So let's imagine that the actual rule says, you know, ABB goes to, you know, BAA or something, BBA, let's say. Okay, so now, yeah, this is easy. Okay, this is easy in this case. The mean field theory, the first order mean field theory just has a probability of A's and B's, right? That's all it does. So this particular thing is just PA times PB squared. See what I'm saying?
Right.
So, and the second order mean field theory considers diagrams and so on.
Right.
Okay. Sharpen the random graph tools. What is the analog of that statement? That there's a probability of A's and B's. That is a certain probability of subgraphs, I would assume.
Mm-hmm.
In a graph, it's a probability for subgraphs. Now, let's think about that in terms of our, you know, hypergraph, ordered hypergraph representation. How do we think about that? Just a minute, I need a piece of food. Be right back. Hi there. Sorry about that.
Right.
You know, in a long string, we could imagine a probability P of B that varies with position.
Right, when you have inhomogeneity in some way.
Right. And we could actually end up with something like a master equation type thing that would say that I mean, the only thing that's weird is that the coordinates are squiggling around. You know what I'm saying?
Mm-hmm.
Which is analogous to this question about continuum limit of string rewriting. That's again what's going to go funky in the graphs, that if we're trying to define, you know, a smooth function for mean field theory, what is it a function of? I'm saying?
Right, there's no canonical coordinate system.
Mm-hmm. unless, well, unless the mean field theory itself defines one somehow, but how do we get that even in a string? So we got a probability P of X, which is the probability of a B occurring, let's say, as a function, but what is X? I think there's some renormalization group thing here because X, okay, so PB of X, imagine that the string has unit length.
Right. So in effect, we're normalizing part specifications in the string to a unit interval.
Right. Then the question is, how uniform is the meaning of X? But in the mean field theory, it could be perfectly uniform.
If one has sufficient homogeneity.
No, but I mean, I'm thinking here. That would be, right, so how would the string rewrite tell you, like let's take the Tui-Morse string rewrite. That's going to make a very messy string. You know what? I remember there's a bunch of renormalization group stuff. But, well, so Tui-Morse is a nested sequence, right? So what?
Well, Tui-Morse is uniform asymptotically, right?
Yes. Well,
So,
it's uniform with respect to n-grams.
yes. So from the point of view of our mean field theory, it should be homogeneous.
Well, only for n-grams of certain sizes. Well, yes.
There will be an order of mean field theory for which it is homogeneous.
Yeah, that's true. I think a Cantor set, on the other hand, Cantor set I don't think should be considered homogeneous. Right?
Right.
I wonder whether there's a literature. I think there is a literature on Tui-Morse lattices. Yeah, that green function. Right, so that's a yeah. Come on, guys, that doesn't take a whole paper to say. It does remind me of When in doubt, look in an obscure part of chapter 10. How could auditory perception be relevant here? Those are the spectra of substitution systems. What is that relevant for? Well, what do we think we could say about, I mean, in the case of our graphs, well, I don't understand how to do this mean field theory thing. I mean, in a sense, it better be the case that the Einstein equation derivation, you know, that is effectively a mean field theory statement, isn't it?
I mean, well, it's an effective theory statement. Whether it's useful to characterize it as a mean field theory, I'm not sure.
Well, let's walk through what it actually is saying. I mean, it's saying that given this graph on a large scale, it does blah, blah, blah. Right?
Right. Or
which is maybe different from.
Yeah, I'm not sure they're equivalent.
Yeah,
they're certainly related.
So the on a large scale it does blah blah blah. How is that related to this functions on a graph type thing?
Well, I mean, it'd better be the case that it's ultimately representable in terms of hyperbolic operators on the graph.
Explain.
Well, I mean, if your claim about, thinking of your claim about the whole index theorem thing and thinking about random walks in terms of, I guess, parabolic differential operators,
yep,
is true, then then I think the analogous thing for the Einstein equations would be defining some family of hyperbolic differential operators on the graph. That would be the way of interpreting the same derivation.
Okay, but that's kind of a flip around, right? Because I mean, one thing is we're saying that on a large scale, the graph has certain large scale properties, right? But now you're saying we can probe those properties by solving some PDE effectively on the graph.
Right.
Right, so the statement is the graph, certain properties of the graph limit to some PDE. That's statement one.
Mm-hmm.
And statement two is if you were to solve some PDE on the graph, what would be true about it? What would you expect to be true about it?
Only some degrees of freedom would be relevant, is kind of what you're saying, right?
Walk me through that. So, I mean, you're saying
when you pick a PDE that you want to solve over the graph, you're kind of implicitly defining something like a mean field approximation, right? Because that PDE will not, in general, care about all possible degrees of freedom of the graph.
I see what you're saying. Although I have no idea what the coordinates in the PDE are.
Right. I mean, again, I guess the PDE implicitly has to define some coordinate system for nodes or subgraphs or something.
How?
I don't know.
Well, it's got to live on the emergent manifold, whatever that is.
Right. So, I mean, in the Einstein equations derivation, there's a way you can define directions and things just by talking about cones of geodesics, which is all you kind of need because they're tensor equations. But in the more general case where you don't have frame invariance necessarily, you have to do something else, and I'm not sure what that something else is.
Okay, let me think about this. Well, okay, but anyway, so all right, anyway, that's a thing for that. All right, one final thing he says. Thinking about quantum mechanics. Oh, actually, this was another interesting one. It was eigenstates in a rules in a states graph, and the meaning of that. Oh yeah, causal nets with boundary conditions. That's another one. I mean, in a states graph with a finite rule, there is a certain cycle structure. Do we believe? Yeah, I mean, clearly there are, in a Wolfram model rule, there obviously are graphs that are sterile with respect to that rule.
Right.
You don't have the right edges and things. And presumably, there are graphs in rules that both expand and contract. There are graphs that are periodic. Well, I don't know whether we care about those eigenstates. I mean, I think we cared about them because we think about quantum mechanics.
Right.
I don't know what they really mean. All right, so in the theory, in the multi-threaded Jonathan theory, I've been trying to wrap my head around what does it mean to say that definite things happen? Okay.
Right.
How would you know that who is part of this multi-way graph? How would you tell from the behavior of the observer or from some other measurable quantity? How could you tell that the observer thought something definite had happened?
Well, looking from the outside, I'm not sure there is a general way of doing that, right? Because the observer has their own, the computation that the observer is enacting in doing their modeling of the universe is not necessarily using the same encoding scheme as the universe itself.
Hence our project.
Right. So I'm not sure there is a, it's like asking for some general procedure to determine, by looking at the physical configurations of particles in a computer, whether a given computation will hold. It's like, without knowing what the encoding is, I'm not sure there's a general way of doing that.
Okay, let's think about that analog, okay? So you're saying, I mean, but that's hopeless then. if what you say is correct, then there is no sort of hard objective way to determine what's going on, right? Then you are left with saying things like, well, if there's been enough convergence, if there are enough sort of critical pairs around and there's enough convergence, then probably the person, the observer thought something definite had happened.
Right.
It's rather unsatisfying.
Right.
Okay, so let's ask your question. The observer.
Yeah, I mean, so we can consider the case where one does have the in effect the same encoding of computation happening in both the observer and the background. In which case, yeah, I mean, all we're saying is that anytime there's a critical pair convergence within the region of the network that we define as the observer, then, from the point of view of that observer, the same critical pair convergence should happen in the rest of the universe.
Wait a minute. The observer is observing the rest of the universe.
Right. I mean, we don't know what that means, but yeah.
Yeah. But so the critical pair convergence is with respect to, as we've defined it currently, is with respect to complete states.
Right.
But we have to decompose these states into pieces in order to even identify an observer as compared to the rest of the universe. So I think the question is, what does a factored critical pair convergence look like?
I see what you're saying. Yeah, so is there some way to make local statements about convergence? Yeah, I guess that is the fundamental problem, right? It's that if you can make local statements within the observer about convergence, then you can ask whether they extend.
Okay, so what does a critical pair look like? A critical pair says this. It's a rewrite statement about hypergraphs, right? Mm-hmm. And it's not about the whole. The critical pair convergence is just a lemma about the equivalence of two hypergraphs.
Yes.
An assumption, a lemma.
Well, the convergence is that, not the critical pair itself.
Right. Well, okay. Critical pair convergence, the statement of critical pair convergence is a lemma about the equivalence of two hypergraphs. Is that a true statement?
Yep, I think so.
Okay. But the observer, so what is the theory then? The observer.
So I think so an eigenstate would then be so the various critical pair convergences will define equivalence classes between hypergraphs. And so then you can ask, for a given equivalence class, what is the sort of canonical representation of that equivalence class? And that will be the eigenstate.
I'm not clear about that. Okay, so first thing is, critical pair equivalences. Okay, these lemmas define equivalences between hypergraphs that generalize the pure isomorphism equivalence.
Right. Yes.
Okay, because
the isomorphism is a static equivalence. This is modulo the dynamics.
Right. Right.
And so,
right. So one of them is that at a particular time, only isomorphism. Go ahead. What were you going to say?
Yeah. No, so my argument is that if the analogy with measurement in quantum mechanics is correct, then what we're in effect saying is that only the equivalence classes are sort of observably distinct.
Exactly.
And so then the parallel would be, as I say, an eigenstate would then be some canonical representation of a given equivalence class. It's the thing that a measurement collapses down to.
Yes. Okay, so wait a minute. So what we're claiming is,
so I think the formalism is, for a given equivalence class of hypergraphs, there will be one that is with respect to the enumeration order, is the canonical one, and that's the eigenstate.
I think that's a very weird way to think about it, because an eigenstate better have an operator that it's an eigen, So
right, but the critical pair convergence we're assuming is somehow defining a measurement operator. Even if we don't know in general exactly how that works.
Well, so you're saying measurement is the essentially replacement, is the quotes replacement, is the conceptual replacement of a whole equivalence class with its canonical member.
Yes.
Okay, now Max and I were talking about the idea, maybe Max can, if he's still with us, can remember. We're just talking about.
Well, just saying that if the evolution of a graph produced two states which are identical, the question is, from an observer point of view, is it a single state or multiple states? If it's a multiple states from observer point of view, then we get classical probabilities based on the number of branches. If they are identical, we have some kind of weights for these probabilities.
Right.
Okay, so wait a minute.
I don't even know how it would work in the situation where you somehow have isomorphic state graphs, sort of spatial graphs, which appear distinct from the point of view of the observer.
Hold on. So unmerged multi-way system. Let's imagine that the true
observer. I mean, the universe could just keep evolving all these branches completely independently. An observer exists in one of them, but they don't know it. In which case, that would be the classical probability case.
Right. Three possible states. Observer. Okay, so classical probability. This is interesting, I think. Classical probability. Observer just picks a branch. Okay.
Yeah.
Okay. Multi-threaded observer. Observer notices equivalence of branches.
Right. And alternative way of saying is that the universe just merges all those branches, which would produce the same result.
Right.
However, I think the problem is that it is global, and it seems very unlikely to be global. So we need to come up with a local version of this.
Well, but let's just consider the global case for a second, which is sort of the analog of few degree of freedom quantum mechanics, I claim. And let's ask the question, with a multi-threaded observer, what is, actually the case where it's really going to get interesting is where we do the combination of two pieces, right? Because that's where we will know the difference between amplitudes and probabilities, I claim. I claim with a single thing, we won't know the difference. What's the minimal case where, in other words, if we have two subsystems, okay, consider two subsystems. In the separate branches case, each subsystem makes its own branches. Look. I think we can make a model of this. Okay, imagine that we have a string rewrite system that is just, let's say, A goes to AA. Okay. Now, in the unmerged case, right, we've got, if we say initial condition AA, in the unmerged case, that will make us, you know, just a pure double tree. I'll get two binary trees, right? Makes sense?
Mm-hmm.
If we don't merge. If we do merge, then we get, what do we get? We get, what's the right thing to draw here? Is this the states graph or is this
we get
the...
a path graph.
Yeah, I know we get I know we get a grid of some kind. How do we draw this? Do we want the causal graph or do we want the state
grid? So
no,
you get a path graph.
I know what we get. I'm just trying to make it actually do it.
States graph.
Yeah, which is the thing that's buggy. Oh God. Infuriating. Anyway, we all know what it looks like. Is there any way we can get a states graph without getting a states graph? Do we have another one? We have an evolution causal graph. Does that show the same thing? Or do we have an evolution states graph? States events graph. What was it called? State evolution events graph.
That's not the right thing. What you actually want is the complement of the, I guess, the evolution states graph with the evolution events graph.
Yeah. Which is otherwise known as a states graph.
Yeah, yes.
Maybe we have to fix the bug. But anyway, but we get the idea. This is a grid. Now the question is, think about this. The probabilities, so it's not a very exciting case, the A goes to AA case. We want something where each thread has something where different threads have different things on them, because then we want to work out, in the one case we've got classical probabilities. In the other case, yeah. Look. What's going to happen is, in one case we got two trees, right? In the other case, these trees will get knitted together. In other words, we get essentially interference between these things.
Right.
So in the unmerged case, we just get multiple trees. and we can compute the probabilities for different by just enumerating branches. Okay, now in the merged case, we have to weight the branches to get the probabilities, right? See what I'm saying? To get the same probabilities, in the merged case, branches will have to be weighted. See what I'm saying?
Hmm.
Okay, what are the rules for those weights? And could it be the case, this is the thought, okay, that as you back out the rules for those weights, you're essentially doing a path integral. In other words, that the rules for the weights would be the equivalent of the rules that you would get were you to do the unmerged case and then look at it afterwards. But you're not doing that because you're trying to make things more efficient. So instead, what you do is you say, I've got the merged case, but then in order to get the same probabilities, I have to look within each thing at many possibilities, right? So they're equivalent ideas, but one of them is calculationally different.
Mm-hmm.
And the question then is whether that calculational difference is, I mean, what the nature of that, how you do that calculation, right? I mean, how do you do it? What do you have to keep track of? And the big enchilada here is, in order to keep track of what you need to keep track of, do you need a vector rather than a scalar, i.e.
Right.
a complex number?
Right. Well, if each edge in the states graph is just a replacement event, aren't you simply keeping track of the multiplicity of the edge?
I'm not sure. I'm not sure because I'm not sure when you combine two, I mean, in order to successfully combine two such graphs, that's not obvious to me. Right? So in other words, we've got two graphs. We've really got to get this working. You got two graphs, right? And how do you knit together those two merged graphs? See my point? If you've got unmerged graphs, it's totally obvious. You just put them all together. You just put
Right.
them. You just arrange them side by side. How do you combine merged graphs?
But shouldn't there be some additive relationship for the vertex degrees when you combine them?
I don't know.
Because I mean, if you have a merged states graph where the in degree of a vertex is 4 or something, isn't that just telling you that in the unmerged states graph there would be 4 versions of that vertex in that level?
Maybe if you keep all the degrees of freedom, it may be less obvious if you don't keep all of the degrees of freedom.
Right. I'm assuming you don't lose any information. So I think it might be as simple as just taking a union of the graphs and adding up the vertex degrees.
There's something here. Look, let's continue just a minute. So one model, see the thing that's a little different and weird is in like the many worlds interpretation, people don't think about that merging, as far as I know. They just imagine that every branch is different.
Right, but the merging is the interference.
Wait, in what model?
As in the merging in our model is equivalent to the, I presume, is equivalent to the interference between branches in the many worlds interpretation.
But there isn't interference between branches and many worlds interpretation. There's just separate branches.
No, there's interference.
No, I thought that in that interpretation that every microscopic event that could go in one of two different ways goes whichever way it goes, so to speak.
Right. But then the idea is that there's some kind of distance relation between branches, and close branches interfere more strongly than more distant branches.
Really?
Yeah. That's the Everettian formalism. That's the whole. That's why in effect you get double slit behavior. Is you're saying the photon is interacting with a photon in some adjacent or like near neighbor branch that's unobservable.
All right. Well, that's okay. Okay, but here maybe that stuff developed since I paid attention to it 40 years ago. That's a little different than I understood it to be. I mean, I understood that the interpretation had to do with what happens when there is a measurement. And what you're describing is what's happening when there isn't a measurement, when it's still just sort of path integraling it out.
Right. I think when Everett first developed it, it was expressed in terms of measurements, but that doesn't seem to be the fashion anymore.
So what is the description now? That there are many branches and that they have interference between branches independent of measurement?
Yes. Or at least that's the way that Deutsch formulates it.
Okay, but anyway, back to these back to these rewrites. Humph. Well, let's see. I think there's something to this. I mean, this business about thinking about merging the fully unmerged case, because there's something very bizarre. I mean, to say that we're doing graph isomorphism all the time is just kind of crazy. This graph isomorphism thing is it's if you have a measurable quantity, it's going to be the same for two isomorphic graphs.
Right.
Or put another way, given a part of the universe, if you then evolve it, if you didn't know that the two things you had were isomorphic, and you evolve it and you measure some property of it, you'll always get the same answer for those isomorphic things.
Yes.
Even though you didn't know they were isomorphic.
Right. Which is why I was saying earlier, I don't see why it makes any sense to say that the observer could, in principle, observe an unmerged multi-way evolution.
No, that's fine. But I mean, I'm saying if the true whatever that means universe, the unobservable universe, if all it's doing is just treeing everything out,
right?
But there is this equivalence between branches that any observer in that universe. Now, okay, look, the fact that the observer is in that universe defines their dynamical equivalence.
Right.
The fact that the observer is in the same universe defines what they will consider to be dynamically equivalent.
By the way, a nice quotation from the Many Worlds Interpretation Wikipedia page. Also, it is a common misconception to think that branches are completely separate. In Everett's formulation, they may in principle quantum interfere, i.e. merge instead of splitting with each other in the future, although this requires all memory of the earlier branching event to be lost, so no observer ever sees two branches of reality. There's also a thing later on that says measurements are treated as a subclass of interactions. There's nothing special about measurements that cannot be dealt with by usual time, unitary time development process.
Time for me to understand more about this. This is obviously advanced a bit since I paid attention. Oh, I wonder what the Stanford Encyclopedia. Oh, wow. Oh boy. Okay, more stuff to understand. And perhaps also some people we should talk to. Is that guy that I've run across? Yes, that guy we have run across.
Saunders.
I think so. Unless it's a different Saunders. And who am I? Oh boy, what did Penrose, Chalmers? Okay, there are all kinds of people we know here. Wojtek Zurek, Hartl. That paper was just unbelievably, incomprehensibly confused, so far as I could tell. Okay, so do you think you understand this stuff, Jonathan?
Well, yeah, to a reasonable degree. That was largely what informed my intuition about completion. Social behavior of a believer in MWI.
What's that? Oh.
There was a section. Oh, this is quite interesting. It's an interesting variant of the quantum suicide experiment.
What's that?
It's a way in principle to convince yourself to an arbitrary degree of accuracy that the many worlds interpretation is correct, which is to, you know.
Oh, I see. It's like make yourself the cat.
Exactly. Yes. And so if each quantum event has a 50-50 chance of killing you, then you can convince yourself to a 2 to the minus n probability of error that the interpretation is correct.
All right. Let's see what else there is here. We should be able to do a direct analog of this. Measuring apparatus M and an object system S. Okay. So each of those is a lump of hypergraph.
Mm-hmm.
What is counterfactual definiteness?
I believe that's referring to if you have a measurement that you could have performed but didn't, does it still have a definite outcome?
Okay, and what does this theory say about that?
I think it needs to be, like, counterfactual definiteness needs to be preserved.
Okay.
Oh, no, sorry, it needs to be violated.
Okay. Oh, for God's sake, poles. That's so stupid. Idiotic.
Proof by consensus.
Yeah, right. With all the advantages of democracy. The largest number of people are happiest, and et cetera, et cetera, et cetera. Okay. Well, so I don't really understand. I mean, and what would it take? Okay, so to make something which is a valid quantum theory in this many worlds interpretation,
Mm-hmm.
what properties does it have to have?
What properties does our multi-way system have to have? What properties does the quantum theory have to have?
What properties does our multi-way system have to have so that you can identify it? I mean, in other words, presumably this theory agrees with existing quantum theory.
Yes.
I don't really understand, but I mean, is there a more formal version of this someplace?
I have some stuff that, yeah, I have some reasonably formal versions of it somewhere. When I was reading about this a couple of years ago, I can probably send you some stuff.
Okay. Do we have any idea if Hofst's cellular automaton thing, which I've never understood, which we tried to understand a few years ago, has anything to do with any of this?
So I was planning to read his paper, but didn't, precisely because I think you told me it was. Well,
it seemed to be. I mean, we looked at it at a summer. Were you there? I can't remember. But we spent a bunch of time at one of the summer schools looking at it.
Yeah, I think it may have been when I was there as a student.
Okay. And the conclusion was it was. I couldn't make any useful conclusion out of it. What the hell is this? Is that a Nathan production? No, it's a differently spelt Meerwald. How extremely odd. That is even more confusing. Nathan's name is hard to spell at the best of times, but the knowing that there's a variant of the spelling makes it even more confusing. Well, okay. Well, I don't know how we make progress on this. I mean,
one test that is in principle possible to do is to check that, well, the sort of my understanding of what interference is actually satisfies the sort of algebraic properties of quantum interference.
How would you do that?
So you set up a superposition so that you have two independent branches in the multi-way system, and then you do a critical pair collapse, and you hope in general that will produce a new state of the multi-way system that was not previously accessible, and then you can check whether the spatial hypergraph in that new state has the states of the two sort of independent things that were in superposition. You can test whether that state graph is compatible with the predictions that get made by standard QM formalism.
Sounds like a good thing to do. Sounds like that's your next paper, Jonathan.
Right.
Well, let's think about that. I mean, yeah. What I'm trying to figure out is for this exposition that I'm trying to write, I want to give, which I haven't started yet. I want to give some indication of how some of this stuff could work, but I'm not going to get deep into it. I want to figure out what the boundary is. Just like I'm not going to get deep into the whole, I mean, mostly my thing is going to be zoological.
Right.
It's mostly going to be, here are the models, this is what they do, here are some properties of the models, here's why they are reminiscent of certain things that are relevant to physics.
Mm-hmm.
Did we work out more stuff about reversibility? Do we think reversibility? I don't think we care yet about reversibility. I think reversibility, I mean, look, there are several things, reversibility, fermions, various things like this, which I suspect are, far down the road.
I think reversibility we do care about more urgently than everything else. Because there are at least, we need reversibility both for time symmetry of GR and for unitarity of quantum evolution. We need some analog of reversibility or some effective theory that gives reversibility.
Look, I think the unitarity statement is a probability conservation statement that I don't think is going to be difficult. I think that's going to end up being. Let me point out something about reversibility. Okay.
Okay.
This is from a long time ago. I have not thought about this since 1980. Okay, in an expanding universe, note that there is a big source of irreversibility.
Mm-hmm.
Okay. And the issue is, what is the interplay between the expanding universe and microscopic reversibility?
Right.
And long, long ago, and I have not thought about this in forever. Let me look at this. Let me look this up. I remember figuring out. So when in doubt, read one's own stuff. Where is it? I guess it will be there. Okay. By the way, for the relationship CPT invariance, CP invariance, unitarity, all slightly different.
Right.
So unitarity is a statement of conservation of probabilities, different from CP invariance, which isn't strictly valid, CPT invariance, which is believed to be valid.
Right. But the point is, this is an old notion of unitarity, right? That we know you can have self-consistent interpretations of QM that violate this algebraic definition of unitarity, but which still have physical unitarity.
What does that mean?
So in PT symmetric QM, you say, you because we start from some non-Hermitian Hamiltonian, your time evolution operator isn't algebraically unitary, and so on the surface it doesn't look like it preserves probabilities. But the point is that the time evolution, when you have a time evolved state, it's still possible in principle to reconstruct what the initial state was, and that turns out to be sufficient.
Sure. So the issue here, if I remember correctly, somehow, well, in this particular case, CP violation enmeshes with the, this is actually a fairly clean paper. I'm pleased with myself here. This is pretty clean. I mean, there's not a lot of crud in here about actual particles and things. And that's probably that's the expanding universe term in the transport equation that then does something. Okay, so what's my point in all of this? My point is that it's not so self-evident. See what happens here. Okay. Huh. Fascinating. Okay. All right. Okay. Back to business. So what you're claiming, that the question is, under what circumstances do you have one-to-one mappings? Can you reconstruct the past uniquely from the future? That's basically the condition of unitarity.
Right. Well, yeah.
We have no idea how true that is.
Right.
I mean, it appears to, it's some random statement that is put into current theories, but how true it is, we don't know. And for example, look, in these models, okay, so the issue with these models is this, okay? So imagine that we are looking at hypergraph evolution.
Mm-hmm.
Okay, think about a cellular automaton. If you well, okay, so the question is, are there two states? Okay, come on, this is easy to think about. In string rewriting, okay, so this is a good question. Okay, so let's reversibility. So a question here would be, what makes a string rewriting system reversible? That would be a first question. And what does it even mean? So let's say that you said, let's say we have AB goes to BA, right? And then if we can only get the stupid states graph working again. We, looking at that states graph, right, we can, what is the signature in that states graph of AB goes to BA being reversible? Is it reversible? It's only reversible in the sense you can get back.
Right.
Now, are there string rewrites which have the property that, yes, I think, okay. If you go to the final state and reverse the rule, can you get back? Right? Under what circumstances can you not get back?
Right. So I mean, I think this ends up just being a very concrete, discrete version of Liouville's theorem, right? That you want every node in the states graph to have one incoming.
Yeah, but it won't be the case. I mean, look. Okay, e.g. for sorting, if you just have a sorted output, there are many inputs that will lead to the same sorted output.
Right.
Okay, so what is the condition? I mean, what happens with cellular automata, right? If you look at the entropy, it decreases for a while, but then you live on this very complicated attractor, and it doesn't go on decreasing.
Mm-hmm.
And how do you measure that? Well, what you measure is once you reach equilibrium, you have effective reversibility, basically. That's the claim. Because any state that isn't going to survive is already gone.
Right.
So any state that has, okay, so this, however, all falls apart in sort of an expanding universe. Because if the total number of states that you can have is increasing, in other words, if you have a fixed set of states, states that can't survive just go away by sort of natural selection. Therefore, the states you have left are not contractive states, if you understand what I'm saying.
Right.
Analogy. I mean, so if I take a random I mean, to see a specific example of this. Okay, there it is. See? After a while, everybody lives on the cycle. And then there's effective reversibility.
Mm-hmm.
That makes sense? However, that won't be true if you allow there to be more possible states as you go, you know, as time moves forward, so to speak.
Right.
For a finite string rewriting system, Um, okay, I'm gonna have to go soon. But for a finite string rewriting system, you are saying, if I say, I think my string tuples function isn't working anymore. I need to get going in a second here. Let's go 1, 0. On tuples, 1, 0, like 5. I bet the states graph is totally broken. I'm confused by it. We have to draw the, I mean, we can draw the analogous thing. It's just the multi-way system. This thing here is simply the states graph of the multi-way system, right?
Right.
So the question is, when is a states graph non-contractive?
Why is it not just in degrees?
It is. It is. I mean, this thing has a, yes, it is. Look at this one.
Yeah, I mean, all you're saying is that if the in degree is greater than 1, then you'll get a multi-way system when you try and reverse it.
Sure. But I'm also saying that I don't think, I mean, this question of whether the thing is effectively reversible, anyway, we have to look at this, and it depends on fixing the stupid bug with multi-way system.
Yeah.
All right, we should wrap here.
Okay.
Excellent. Look forward to seeing what you come up with, Jonathan. I realize it's the middle of the week for you. It feels like the weekend for the rest of us. I'm going to work on a variety of things here. I will be around later, Max. If you happen to be around, you can send me mail, whatever. I'll be out for a few hours.
Okay.
And then I look forward to seeing your stuff, Jonathan, and keep your academic dogs at bay.
Right. Yeah, but I'll be free to work pretty much all weekend if you are around.
Oh, I'll absolutely be around. So but I think the main thing for you is a bunch of code. So I'll be around. And look forward to seeing what you have.
Okay.
All right. Talk to you all soon.
Happy Thanksgiving.
Oh yes, thank you. Same to you. And what is the British analog of that? There's some crazy harvest festival they used to have at least when I was a kid.
Oh, I'm only dimly aware of this. It's certainly, yeah.
I don't think it happens in the cities. I think it was more of a country phenomenon, and I don't even know when it is. It's probably at the time of the harvest or something, which probably happens
not now. Yeah.
Right. Okay. Anyway, see you guys.
Talk to you soon. Bye.
Okay, bye. Bye.